All right, here we go with the next unit. This is chapter 3, which talks about polynomials and rational functions. To warm up, I just want to start off by sketching each of these graphs. This first one, we've got y equals x. This is the parent function for a linear function. So the shape of this graph is a straight line through the origin that is diagonal, of course a slope of 1. This is a linear function. Next up, we have y equals x squared. This is the parent function for a quadratic. So the shape of this graph is a U shape. It's curved. It goes upward in the positive direction, and it also goes upward in the negative direction. Y equals x cubed. This is the parent function for a cubic. In the positive direction, it curves upward, and in the negative direction, it curves downward. So we get kind of this S shape. For y equals x to the fourth, this is the parent function for a quartic. Again, it's a U shape, but now it grows quicker. So the shape of this is going to be, the slope of this is going to have more of a steeper growth rate. So something like this, x to the fifth, this is the parent function for a quintic. This is going to be that S shape again. It's going to grow in the positive direction. It's going to decrease in the negative direction. Again, that slope is going to be pretty steep. So again, we're talking about polynomial functions. So I just decided to give you just the definition for a polynomial function just as a refresher. Again, a polynomial function, we define this. This is the general form for a polynomial of degree n. The numbers in front of each of our x, our variable, is called coefficients. The last one that has no x, this is the last term in the polynomial, written in standard form, is the constant coefficient or the constant term. For the purposes of this class, I'm just going to refer to this as the constant. The number an in the first term is our leading coefficient. So that's the number all the way out in front on the highest degree. Furthermore, polynomials are smooth continuous functions. So examples of graphs that are not polynomial functions is something like this, where we've got a hole or a break in the graph. Corners and cusps are also not found on polynomial functions. These two are examples of polynomials. They're smooth, they're continuous, they're nice and round. So I want to start off by graphing each of these functions here on your Inspire calculator. So here I have 4 functions. Go ahead and punch each of these into your Inspire calculator. I recommend creating 4 separate pages so that you can reference each graph. So take a minute now, pause the video, and plot each of those functions. So I've gone ahead and plotted each of these functions here. Let's look at the first one. Here we have 4x squared minus 3. The degree of this polynomial can be found by the highest exponent. In this case, the degree is 2. The number of zeros here are, the real zeros here are on the x-axis, so these are our x-intercepts. This function has 2 zeros. The end behavior, this is as x gets really big, as x increases or approaches infinity, what happens to the graph? Well, as we increase x, the function grows and grows and grows. So we can say that as x approaches infinity, y also approaches infinity. As we move in the negative direction, as x becomes greater and greater in the negative direction, the function increases in the positive direction. So the function y approaches infinity. So as x approaches negative infinity, y approaches positive infinity. Let's take a look at the next one. So here we've got x cubed minus 5x minus 2. The degree of this polynomial is 3. We can count the zeros, the x-intercepts. We have 1, 2, and 3. As we move in the positive direction, the positive x, our function increases in the positive direction. So as x approaches infinity, y also approaches infinity. As we move in the negative direction, the negative x, our function decreases. So as x approaches negative infinity, y approaches negative infinity as well. Taking a look at the next one, we've got x to the fourth plus 2x cubed minus 6x squared plus 2. This is a polynomial of degree 4. We count the zeros. We've got 1, 2, 3, and 4. So there are 4 zeros. And as x increases, our function also increases. So as x approaches infinity, y approaches infinity. As x decreases or becomes greater in the negative direction, our function increases. So our function becomes greater in the positive direction. So y, as x approaches negative infinity, y approaches positive infinity. And last but not least, we've got our quintic. This polynomial is of degree 5. Count the zeros. We have 1, 2, 3, 4, and 5. As x increases in the positive direction, our function also increases. So as x approaches infinity, y approaches infinity. And as x approaches negative infinity, our function decreases. It approaches negative infinity as well. Now take each of these functions and make the leading coefficient negative. Let's see what happens. Looking at each of these functions, let's take a look at the polynomials with even degree. So this would be the quadratic and the quartic. When the leading coefficient is positive, we notice that the end behavior, as x approaches infinity, f of x also approaches infinity, or y approaches infinity. As x approaches negative infinity, y also approaches positive infinity. But when we make the leading coefficient negative, so we'll make the quadratic negative and the quartic negative, we notice that it flips our graph. So now, as x approaches infinity, y approaches negative infinity. And likewise, as x approaches negative infinity, y approaches negative infinity. Looking at our polynomials of odd degree, so this is our cubic and quintic, with a positive leading coefficient, as x approaches infinity, y approaches positive infinity. And as x approaches negative infinity, y also approaches negative infinity. But as we make the leading coefficient negative, so the number out in front, we see that as x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches positive infinity. Notice that for even degree polynomials, the end behavior is the same on both ends. So for example, when the leading coefficient is negative, the function approaches negative infinity in the negative direction, and it approaches negative infinity in the positive direction. When the leading coefficient is positive, of course it approaches positive infinity in the negative direction, and it approaches positive infinity in the positive direction. For odd degree polynomials, the end behavior is the opposite in either direction. So when the leading coefficient is negative, as x approaches negative infinity, the end behavior is that y approaches positive infinity, and as x approaches positive infinity, y approaches negative infinity. And vice versa if the leading coefficient is positive. Alright, so let's actually get to graphing. Here I've got the function f of x equals x squared plus x minus 6. This is a quadratic. Immediately I recognize that we can factor this quadratic. So factoring this, we have x plus 3 and x minus 2. Again, this is a quadratic. The parent function is f of x equals x squared. The degree of this polynomial is 2. And using the zero product property, we know that the zeros for this function are at negative 3 and positive 2. So our x-intercepts, we have negative 3, 0 and 2, 0. So already we can plot those points. 1, 2, and negative 1, 2, 3. Our y-intercept we can find from the original equation is negative 6. So that's if we were to plug in 0 in for x, we get 0 squared plus 0 minus 6 is negative 6. So we can plot this. We sketch the graph and we get this quadratic. The domain is all real numbers, so we get from negative infinity to infinity. The range, plugging into your calculator and finding this minimum, is negative 6.25. And of course, it goes all the way up to infinity. The end behavior, so as x approaches infinity, so positive infinity, our function f of x approaches positive infinity as well. As x approaches negative infinity, our function f of x approaches positive infinity. So let's talk about multiplicity of zeros. Here I've got the function f of x equals the quantity x minus 2 squared. So here we see that the graph has a 0 at x equals 2. This function seems to bounce off of the x-axis and come straight back up. So it's coming from the positive direction, it hits the x-axis, hits 0, and then it bounces back off into the positive direction. Let's see what happens when we change this exponent here. Let's change it to 3. So it comes in from the negative side, it hits 0, and then it goes off and continues on to the positive side. So this, when the power is 3, it doesn't bounce off the x-axis. So this is what we call the multiplicity of a 0. So back to this example here. This 0 at x equals 2 has a multiplicity of 2. This here has, at x equals 2, a multiplicity of 3. If you were to take this and expand this exponent out, so say x minus 2 times x minus 2 times x minus 2, we get that this 0 at x equals 2 occurs, quote unquote, 3 times in this function. So that's why we say that the 0 has a multiplicity of 3, and in this case, 2. So let's formally define what multiplicity is. We can say that if c is a 0 of a polynomial p, where the corresponding factor and that factor is the quantity x minus c. We're saying that if that occurs exactly m times, in the factorization of p, then c is a 0 of multiplicity n. So however many times this factor occurs, the 0 occurs in the factorization of the polynomial, we say that it has that same multiplicity. Examples, so like what we explored, say we have f of x equals the quantity x minus 2, and that quantity is squared. We get a graph that looks like this, where the 0 is at x equals 2, and it bounces off. In particular, when the multiplicity of a 0 is even, then we call that a bounce. When the multiplicity is odd, so f of x equals x minus 2 raised to the third power, that passes through the point at x equals 2, we get this shape here. So let's practice what we know about multiplicity and graph this function. So here we've got 3x's here, this is x cubed, and then this is x squared. So we know that there are in total 5 x's. The degree of this polynomial is 5. Therefore, the parent function is a quintic, x to the 5th. We know that we have zeros at positive 1 and negative 3. So let's go ahead and plot those. Positive 1 and negative 3. We know that we have a bounce at x equals negative 3. And then we have a multiplicity of 3 at x equals 1. let's go ahead and plot those. So our x-intercept is 1 and -3. Our y-intercept, we can plug in 0 in for x. So plugging in 0, we have f of 0 equals quantity 0 minus 1 cubed times the quantity 0 plus 3 squared. And so we get -1 cubed is -1, and then 3 squared is 9. So we get a y-intercept of -9. So we can plot that point. So again, we have a bounce at -3, and it passes through +1. We know that the leading coefficient is positive, so our end behavior from as x approaches negative infinity, we should be coming from the negative side. So we're going to come up from the negative side. We're going to bounce at -3, so it's going to come back down. It'll come up, it'll pass through the y-intercept, and then it'll pass through the other 0. So we get a function that looks like this. The domain is all real numbers. That's true for all polynomials. The range for a quintic is also all real numbers. So from -infinity to infinity. And the end behavior, as x approaches positive infinity, our function f of x approaches positive infinity. As x approaches negative infinity, our function f of x approaches negative infinity. Again, just a quick recap on how we sketch this graph. We notice that the function has zeros at 1 and -3, so we plotted each of those points. Algebraically, we can solve for the y-intercept as well. That's where x equals 0. So we get these 3 points here. And analyzing the multiplicity of each of these zeros, we can draw the general shape of the graph. We know that at x equals -3, we have a bounce. The multiplicity is even. It's 2. And then at x equals 1, we have a multiplicity that is odd, so it passes through. We know that we're looking at a quintic, and the leading coefficient is positive. So we're starting in the negative direction. As x approaches negative infinity, our function should be negative. As x approaches positive infinity, our function should be positive. So we're generally moving from the bottom left, from quadrant 3, up into quadrant 1. The last thing that I want to talk about today is the intermediate value theorem. Just a quick little theorem. What the intermediate value theorem says is that if p is a polynomial function, and p of a and p of b, so those are two x values, a and b, say they have opposite signs. So one's negative, one's positive. It doesn't matter which one is which. Then the intermediate value theorem states that there exists at least one value c. So that's another x value c that is between a and b, for which p of c equals 0. So let's see exactly what does that mean. So say we've got a graph here. We've got a function where we've got a is here, b is here, and we'll just say, we'll just pick that p of a is negative. We'll say that it's down here. We know p of b, we'll say it's got to be opposite signs, so we'll say it's up here. And we know that it's a polynomial function, so it's smooth and continuous. So we're coming up here. So for some interval a and b, the intermediate value theorem states that there exists at least some point between a and b, we'll call that point c, such that p of c is equal to 0. So it's saying that if there are opposite signs on an interval a and b, that somewhere in the middle of that interval there exists a 0. So let's practice. Let's use the intermediate value theorem to show that this function has a 0 on this interval from -3 to 2. In order to find this, let's find what is f of negative 3. So what is that first value? So at negative 3, we have f of negative 3 equals negative 3 minus 1, quantity cubed. Negative 3 minus 1 is negative 4. We cube it, and we get negative 64. So f of negative 3 is negative 64. F of 2 is the quantity 2 minus 1 cubed. Well, 2 minus 1 is 1. Cubed is still 1, which is positive. So we can say that since f of negative 3 is equal to negative 64, and f of 2 is equal to 1, since these have opposite signs, there exists a c. So some point c, where c is between negative 3 and 2. So negative 3 is less than c is less than 2, such that f of c equals 0. So that's the intermediate value theorem. All right, so this is part 1 of polynomials. We're going to get a lot of practice on this, and then join me for part 2. Have a great day, everyone.